Hello everyone, today I am going to deliver another lecture on shear, bond and bearing. The lecture in contain at first the shear with general consideration, and I will show the figure of shear carried by concrete and tendon, and then I will showing the figure of development of cracking, and then I will discuss I will discuss the shear principal stress, and then I will discuss the shear ultimate strength of beam, and I will showing the broadly math example of shear. Check the shear strength cracking of beam. It could be three examples, and then I will demonstrate the shear wave reinforcement and showing the example of the steer example of the design of the stirrups following a CI put, and then showing the flexural bond and intermediate point, and then showing the pre-stress trans- transfer bond in pretension concrete, and then showing the bending at anchorage, and then demonstrate the transverse tension at wind block, and last one I will discuss the torsional strength. So let's start the shear of tendon. Okay, let's start. So before I'm starting, I'm just giving the reference that all the important notes are taken from this book, which is Design of Pre-Stress Concrete Structure Third Edition (TYD). So let's start the first topic, shear, with the general constitution and figure of the shear carrying concrete and tendon. Okay, we can see here the shear. So before I'm going to shear, I'm just discussing the shear general constitution. Okay, let's go there. Okay, there we can see in this book the showing here the shear. The strength of pre-stress concrete beam is flexure is required, definitely knowing, but their strength of resisting shear or combined of shear flexural cannot be predicted corresponding precision. Previously, about 1955, a numerous pre-stress concrete beam has been tested on their strength and flexure, but very few in shear. Okay. So between 1955 and 1961, however, the 100 of the specimen were actually tested in determine the strength of resisting shear moment and shear without reinforcement. Okay, so let's see here. We can see some formula is given there. We can see BC equal to B into B BP. So we can see here the shear carried out the concrete, the beam. We can see first diagram. This is the diagram. The beam with straight tendon. The tendon is straight, and the shear is going downward. I'm just seeing from here. The shear resistance only by concrete. This is the shear resistance only by concrete, and then we can see here beam with the inclined tendon. So tendon, you can see this is the inclined tendon, this is the section of B, this is the section, this is the BC, which is critical shear, and this is the BP, which is pumping shear. So we can see another figure is C, which beam with inclined axis but straight tendon. So tendon, we can see tendon are straight, but the beam is inclined, so beam is inclined. So you can see the two sections C even D, C and D both are same, so there is going the downward. Okay, let's see here the shear carried by concrete. You can see the shear resistance is only by concrete. We've been seeing in first graph, which is beam with straight with tendon. This is the beam with straight with tendon. Another is beam with inclined tendon. So you can see second one, beam is inclined with tendon. This is the shear resistance concrete plus vertical steel. It will be shear will be resisted by. And third one, we can see the beam with inclined axis but straight tendon. So you can see tendon it is straight but beam is inclined. So shear resistance only will be tendon. Okay. So these are the also in that, and the first figure of the shear carried by the concrete and tendon is also in that. Now we'll see the figure of develop of the shear cracking. So let's see here. So you can see the develop of the shear cracking in here. You can see this is the flexural crack. Here the 2-point load is given here, and the flexural crack is appeared in the mid of the beam, and the web of flexural crack we have been seen is the 45 degree and the vertical. So vertical crack is flexural crack, and the web crack is the 45-degree angle. We can see here the web crack is 45 degree. When the 45 degree plus vertical crack, then we can see the flexural crack. Okay. So the shear force diagram will be like this for two-pin bending. It will be upward for reaction, and it will be upward reaction. So we will go the upward reaction, and shear force will be like this. After getting the shear force, the area of the shear force will be the bending moment. So bending moment will be shear force. So we can see the maximum shear points. The shear crack will be appeared. So we can see this is the maximum shear force. So the shear crack will be appeared due to the maximum shear force. On the other hand, we can see the flexural crack. Flexural crack will be induced due to maximum bending moment. So it will be keep in mind in your head. Okay, so let's see here in this book. So you can see bearing inclined and tendon carrying shear. You can see here the beam with no shear in concrete. There is no shear, and continuously beam with concentrate load. This is the concentrate load, and carb free-stress steel. These are the development of the shear cracking. I have been already discussed. I am saying again. This is the cross section, and this is the initial flexural crack of P. P means load is slightly more than service load for typical beam. This is the typical beam. So you can see the web crack is appeared in at the point of the what I will say the support, and web crack is support. And we can see the inclined flux use the shear cracking. This is the inclined flux. Okay, the flexural and shear cracking at the factor load. This is the factor load. So this is the moment diagram, and this is the shear diagram. I have already shown this picture. Okay, so I hope that these are the in depth. So let's go to the shear, the principal tensile stress. Okay, so if you go there, you can also the inclined tension crack is origin in wire. These are the origin in wire. So inclined tension crack in origin will form flexural crack. This is the flexural crack. Inclined crack is here. So now we'll see this person principal shear in principal stress for this part. Okay, so conventional design for web shear cracking and free-stress concrete beam is based on the computation of the principal tensile stress in the web and the initial stress of the certain specimen below. Okay, so the first part of this method is compute the principal tension based on the classical approach. Is correct procedure is so long as the concrete has not cracked. Okay, concrete will be not cracked. There is some formula. We can see the total external shear which is B, and the deduct the shear BP is carried the tendon obtain the shear which is the carried of the concrete carried by concrete. So it is the concrete shear equal to total shear into minus the shear carried by tendon. Okay, so we can see here the shear stress BQ by IB, and another we can see formula for here. So this is method for the combining for step 1, step 2, step 3 for the stress getting here. And ultimately we can see the beam with the using free stressing. This is the mode circle of the stress in element A. We can see here the mode circle, and the element A from the above. We can see here the C is the compression, T is the tension. This is the BC, the concrete shear, and BP in tendon free stress shear. And state of the loss of concrete we've been seen here, and another formula we've been seeing this. And we can see an example is here. Also I'm just skipping here. uh, we can see another example is given here. I'm just skipping, I'm not elaborating. So these are the index. So we can see here the shear ultimate strength of for beam. This is the important. So I will see. Okay, this is the shear, the ultimate strength from beam. The as we discussed previously section, the conventional method analysis, the principal tension uh, based on the state stress homogeneous material is rational method analysis as long as the concrete has not cracked. So these are the concrete will be not cracked. However, if the service load limited value set for designing the member is proportional will causes different factors safely. Slightly increase the loads in procedure approaches and varying the incline in the principal tension and resilience, while the resilience of concrete principal tension may also change with the magnitude of the compressible fiber stress. Okay, so we can see here. Now we can see another which is the analysis for the shear stress distribution of shear along with the span. So you can see this is the support, and this is the CGS, which is centered of steel, and the load is there given there 1.4 dead load plus 1.7 live load, and B is given here, B ultimate minus B concrete equal to B ultimate minus B CW, and found all of the here distribution span along the here. Here is some the fiber equation showing 1977 as per ACI code, and the shear force equation. This is the shear force equation. This is the shear force equation, and the same 1977 act, and B and equal to 5 B1 into 5 BD, and given all the diameter, all the equations. So if we see in here the ACI equation for shear evaluation, we know the stress, which is the shear force into B into D, and the factor for free stress we've been taking the 0.75, others we 0.78. On the other hand, we calculate the normal RC, then we'll taking the 0.75, but free stress we've been taking the 0.85. Okay, let the shear stress, which is 0.29 F prime C, this formula is used, and these are the frequently we will use, which is the shear force. With this formula it will be used, and flexural or inclined stress we can use this formula, and flexural inclined force we can use this formula for taking the for getting force. Okay, here is an example. So let's see, the equation of OF is given here, and this equation is given here for shear equation for here, and the stress is given here. You can see here the relation between nominal stress at the web cracking and compressive stress at the centroidal. You can see in x-axis FPS of F prime C, and y-axis CW divided by F prime C, and this line is dotted line is this equation, and the straight line is this equation. Okay, so another formula we've been seen here, and this one. So let's see an example from here. Check the shear strength for the beam shown in below. This is the Z section is given x distance, which is L, which is 0.5, and all the length is 15, which is h by 2 from the support. The given that the section is adequate for W 70 kilonewton per meter on the basis of the flexural strength. Compute is example 5.8 is given here, and F prime C is 49 ampere. So you can see on this is the section which is B is 450 and D is 750, and the location of CGS is 150. Okay, so there are in the bottom section we've been seeing the 12 piston, and we can see, and the top fiber is 6 steel. So total we can see 18 steel. Okay, so let's start. We can see is given F prime C 49, and S is still area is given, and Fs is given, and section of moment of inertia and area is given from taken the example, previous example. And force, now we can calculate the force. So we know the force equal to area into stress. So we know the area of steel and stress. So if we multiply this, then we will get the force. Remember, the force is total of 12 plus 6, which is 18. For 18 tendon, this force. If we calculate for only 6 tendon, how we calculate? We will calculate from using this formula. Okay, so we can use for only 6 tendon. I will calculate. We know that total 18 tendon. We know this form this below on 1989. So 1989 divided by 18 and multiplied to 6. Then we will get the 6 tendon. Okay. Now we will calculate the stress and free stress concrete, which is using this formula. Force into area. Force means area into stress, and putting this below and founding this. Okay, let's see. Now we can calculate here the web shear force using this formula. We can using this formula, and after before going to the this using this formula, we have to find out the pre-stress shear. How we calculate pre-stress shear, which is 13.26. So you can see 13.26. As we have been found the only for 6 tendon force, we have been found 663. This is the 663. It is the distance from left section is x, or we can see h divided by 2, and we have been found here. And we know the total length is 15, but in the middle portion we have been seeing the 17. This is the 17, and this portion is 1.5, and 1.5 is given here. So if we deduct from 7.5 to 1.5, then we can found in this portion 6. So if we deduct 6 minus 1.50, why we will deduct the 0.50? Because of the this is the x, which is h divided by 2, which is 0.5, and found the value is 5.5. So we can see this value is 5.5. Hey, so this value is 5.5, and the height we have been found 110 and 109. How we'll get? So we can see this is the we have been found the 300. So we have been divided in two portion, 110 and 195. So that's why we have been divided in this way. Okay, how we'll get this? This is the 300 we have been seen in the right portion. So that's why this is the 300. Okay, so it will be divided in two portion. So I will calculate BD. This is the most important. So we know the for 6 tendon, which is 663, and this is the length, which is 5.5 meter, and we will be converted in millimeter. And height we know this is the millimeter is given 110. In this way we can calculate the free stress shear, which is 13.26 kilometer. Okay, we just putting this value and all the data we have been finding here, and finding the web shear reinforcement, which is 493 kilonewton. So require resting for web reinforcement. Okay, so now we'll calculate the ultimate shear, which is Bu at the h divided by 2. We can using the formula W into divided by 2 in minus W into x, and after the what will be x? X is nothing but it will be h divided by 2, as we have been seen in previously, which is 0.5, and putting this value of x, and funding value is 490 kilonewton. And now we can calculate the ultimate capacity, which is BC, and there is nothing new formula is arise. We just divide the ultimate shear with the multiplication factor is 0.85. Why we are dividing 0.85 not instead of 0.75? As I have been already mentioned that in the RCC structure or RC structure we have been use the multiplication factor is 0.75, but in contrastly, as we have been calculating the free stress, that's why we have been taking the more safety, which is the 0.85, which is the greater than 0.10. Okay, so ultimately we have been found ultimate capacity 567 kilonewton. So therefore we can see the ultimate capacity is greater than which is B shear, which is shear web shear reinforcement. So we can say the ultimate capacity is crossing the limit of the web reinforcement, which is we've been found in previously here web shear force, which is 493. So that's why we have to use the stirrup. So we can conclude that the web reinforce are not needed. If needed, then how can we calculate? So if the shear force is needed, we can let's assume the shear the ultimate capacity is less than the shear. So if we have in found like this, then we can calculate the shear reinforcement is required. So we can see here the leg length. If we use the leg length 2, then we can use multiply with 2 the area of the reinforcement. If we found the leg is 4, 1, 2, 3, 4, then we will multiply with 4. Okay, so let's take the reinforcement, the area of bar, which is 3 to 8. As we've been using 2 leg and using only 3 number bar, which is 10 millimeter, and founding this value, which is 0.11, and multiply to the stirrup. So 10 millibar we've been using 2 leg stirrup, and spacing we can use this formula, and after the putting this value we've been found the spacing 101 millimeter, and another which is found as max is 0.75 into x, which is found 563 millimeter. So between 1 and 2 we've been found the minimum is 101 millimeter, so we can use 1 millimeter. Okay, I'm just giving this example. So one example is in that. So now let's see another example. So check the shear reinforcement section is given. Judges section for the beam is shown below. Here is the beam, and the I shape is non-composite. These are the non-composite section of span is 15 meter, and the CGS is 113 from the bottom of fiber, but the station judges section is given. This is the 6 meter. In previously we've been seeing the judges section is 0.5, but in this case we've been seeing the judge section is 6 meter. Okay. Other information is given for the beam. We've been seeing all the information given here. So now we can calculate the shear at D, which is the depth of shear. The shear due to the dead load, we can see WL into L, as the cantilever is acting here. W into L divided by 2, and W into X. What is the value of X? X is nothing but it is the section of the from left side, which is 6p. Okay. I will calculate WD. W is nothing but area into concrete unit weight, and found 5.6. Okay. And putting this value and found this value. Now we can using this formula, as we have been seen in previously when I have been introduced at first. Then we can use the ratio of this formula. So using this formula, W into L into X divided by 2 into L into X divided by 2. If we taking the W into 2, so it will be common value, and it will be also common value. So it will be cancel out. After the cancel out, we can found this value, this formula. So we'll using this formula, and after putting this value, this is the ratio, which is moment divided by shear, which is 18 meter or 18 into 10 to the power 3 millimeter. Okay, let's see. We can use the stress of 3 stress using this formula, and I will calculate Y while found H divided by 2, as we've been seen in H in previously. Here this is the 750 into 150. We just using this and divided by 2, and 900 divided by 2, which is 450. It will be 450. Okay. And after putting this value, all the value, and forming this way, and now we'll calculate the stress and dead load, and found My by I. How will calculate M? This is the formula we've been using, W into L, and this is the force into perpendicular distance, that means X divided by 2, and this is the force and this is the perpendicular distance. I am putting this value and founding this value. Now we can use the moment, critical moment, and we use yt. I will calculate yt is divided by 2, which is 450. I am putting this value from putting all the values and found ultimately this value. Now you can see the inclined, which means OF and flexor. This is the inclined OF plus flexor. For shear force, we can use this formula and found 10.93 kilonewton. Okay, for now we can calculate ultimate shear. This is the ultimate shear in the section Z. We can see this is the schematic diagram, and W into L divided by 2 into W into X, as we have been deducting here, and found 105 kilonewton. And ultimate capacity PC, we know it will be divided by factor load, and found 123 kilonewton. So 123 kilonewton is greater than 1 CI, which is 109. As we have been found, this is the 109 OF inclined OF shear force. So that's why you can see shear reinforcement is not needed. If the shear force is needed, then we can use this formula for calculating the shear reinforcement. Okay, let's see another example here. The check the shear strength for the beam shown in the below. The adjust section is given here, which is H divided by 2. Support is given, which is 0.5. This section is adequate for this value, and basis of the flexural appearance is given. So we can see here 12 still and 6 still is here. So you can see this value and this value is given, and we can calculating the moment of inertia in area, and now we calculate the force, which is 8.2. So if we found so FPS is given here 1105 for total. We can see 12 into 6, which is 18. Now we'll calculate for only 6 force. I will calculate it will be nothing but divided by 18 divided into multiplied with 6, and found this value. Now how will now we'll calculate the BP. Now we'll calculate the web shear force. It is vital important to calculate the shear preceding shear. I will calculate. So these are the common what I will say. It is comparison. BP divided by vertical. So BP divided by vertical. F6 divided by horizontal. X is divided by these are the horizontal. So BP will unknown, and vertical 139. So you can see this is the 139. As this portion is total is given. We've been seen is divided by 2, which is given here. 139 into 195. This is the total length, and this is the 139. Okay. So 139, and F6 is found is here, and horizontal distance we've been found 550, as we've been seen here. I will calculate, and we know the total is 7, but total is 15, but the half portion is 7. If we deduct the this value, then we've been found 6. If we deduct 6 minus 5.5, if we deduct this value minus 6, which will be 0.5, then will be found 5.5. After this and found 5.5, that means 5500 millimeter, and found BP this value. This is the share of P, and finding this value, and we just putting this value all the dimension. After the putting all dimension, finding this web shear force, and then we can use the ultimate shear force at H divided by 2, which is WL into 2 into minus H into X. What is the X? X is nothing but this is the value of 0.5. That's why we will use 0.5, and founding 495. And ultimate capacity will be divided by factor load, and found 576. So you can see the 576, which is the capacity, is greater than the web shear force, which is 525. So that's why no shear force is needed. If it will be vice versa, then shear force will be needed. So this portion has ended. So You can see another example from here, from this book. In the same way, we can using this information finding the stirrup required load is here, and on the data is given here. I have been seen all the data is given here. The another calculation is given here, and the plot the shear force and distance of the along the span is given here. Now we can use the shear web reinforcement. We can go there, share it web reinforcement, and math example of the web reinforcement. So let's start the shear web reinforcement. The since we do not understand completely the behavior of stress or reinforcement concrete beam without web reinforcement, it is obviously more difficult to analyze those web reinforcement. Okay. So fortunately, the firmly extensive series of the tests have now been conducted in symmetrically method have been for the formulated which for allow design and share to be made conversely. Okay, so we can see here BS using this formula for getting the design for the shear reinforcement, and the plot diagram we also here, and another formula we've been seeing here BS equal to in this formula. So ultimate design for the combined moment and shear, we can see these are the moment nominal, which is ultimate divided by phi, and we can see this is the spacing of the spiral bar, and this is the force. We can see stress. This is the stress. We can see area into force, and this is the tension force. This is the compression force, and this is the shear in concrete, and this is the lever arm JD, and this is the D. Okay, so we can see here the some formula ACI code method, and we've been using this formula also, this formula and this formula, and this formula for ACI code express minimum AB for this formula. Okay, so these are the ended. Now we can see the another which is the math example of the designing stirrup following the ACI code. Okay, let's see, these are the example. So design the stirrup following ACI code for the beam example is given in previously. Use the plot shear stress is given also in previously, and solution assume the stirrup perpendicular to the longitudinal axis Fy is 50 ksi is given. So solution we've been using using 3U 2 leg stirrup, which is AB is 0.22, and figure is given, and we've been found BU divided by 5 into BC is 17.5. So after putting this, and we can use this formula and found this here. So I will we just using the alternative changing here, so that's why it will be changed S, and BS found is 17.5 is given here. So if you go to the how will calculate how will finding 17.5, if you go to the 257 where is 257, okay, these are the 257, and this is the value we have been seen. After getting this value, we just calculating here is required BU divided by BC, here is found 17.5. Okay, we're taking this value for calculating here, and founding the ultimate spacing is 18.9. And another we can see from support, which is given BCU 9.8 is given also in here. From we're taking 9.8, this is the 9.8, and from section A 15, the distance is given is 15 feet. So if we go there and putting this below 9.8, and this is the 9.8, and found the spacing is 34.9 inches square, and another which is ACI code is provided 24 inches square. So after we've been finding three spacing, which is 18, 34 and 24. So you can see it is greater than 34, so we can use the 24. So spacing control the except at the end we have been using this formula and finding AB is 1.13, but we have been used 0.22. But we can see here is a 0.22 is here as 2 leg, as one leg, one AB is 0.11, but we are multiplying is 2, that's why it is taken 2 2. So it is okay. So these are the our recommendation. We have been seeing 34 is greater than 24, so that's why you can see use 3 number 3 bar using uh, U 2 leg stirrup at 20 inches square spacing for entire beam except two spaces of 16 inch at the each end, and place fast stirrup no more than 8 inch square from the end. Okay, so these are our um, recommendation. So it will be finished. Now we can see flexural bond at intermediate point. So here flexural bond at intermediate point, we can see here some theoretical, we can see all the theoretical, there is no math example. Okay, so for the free-stress concrete bond is supplied by the grouting. For pre-tension concrete bond is secured directly with the place of the concrete. When the bond at an beam is subjected to the shear, bond and stress are produced. In order to design against the bond failure, it is necessary to determine two things. First, the amount of bond stress existing between steel and concrete, and second, the bond rest is between two materials. Okay, so you can see here these are the inlet. Now you can see pre-stress transfer bond in pretension concrete. Okay, so you can see here pre-stress transfer bond in pre-tension concrete, nature in the bond and length of the transfer. When tendon are pre-stressed and their stress is often transformed into the concrete solely by bond between two material. Thus, there is a length of transformation at each end of those tendon to perform a function anchorage when the mechanical end and anchorage are not provided. Okay, so we've been seen here pre-stress transfer at the end of the pretension beam. Here is a F from the bulk cord before the transformation here, and shaking of year after the transfer, and this is the X value and LT, and B is the section and A is the end section. And we've been seeing this is the LT is given here, which is the length transformation using this formula. You can use this also LT divided by me. So transfer length we've been seen here. This is the transfer LT, and transformation length is here in schematic diagram and free body of wire. We can see here the flexural bond overlap with the transformation length. This is the distance, and flexural bond is LB, and flexural length is LT is given here B into B. Okay, this also in that. Now we can see bearing at anchorage. So we can see here the for the tendon with the anchorage, there will be pre-stress in transform into the concrete by direct bending. Various design may be used to transmitting the pre-stress plot steel block and remaining concrete tendon concrete ones. Okay, we can see here the some step is given following grouting, and formula is given here. We can see here the an example is given here. The example is given here. This is the area is given here, and we can use this formula. Now these are the inlet. So you can see transverse tension at in block. So this is the transverse tension at in block. The portion at the pre-stress member surrounding by anchorage on their tendon at tendon is often termed the in block. Throughout the length of the in block, the pre-stress transform from the more or less concentrated area of the distribution throughout the entire of the beam section. So the theoretical length of this block is distance throughout which is changes the takes the place is sometimes called in the lead block. Okay, we can see here the stress at the in blocks. The variation of Fy in along the along the x-axis. We can see the in beam. This is the in beam. This is the x, and tendon is here, and this is the x, and fiber stress at B. This is the point of B, and shear stress at B. This is the point of B. This is the and tendon is here, and one tendon is here, and second tendon is here. And the variation of Fy is x-axis here, A section is here, B section is here, fiber stress and shear stress both are s-axis, and compression is in upward and tension is downward. We've been seeing here. Okay, so you can see here the isobar for transfer tension in block in terms of the average comparison and shaded area represent the compressive zone. This is the shaded area, compressive zone. This is the shaded area. And from the Goyan's pre-stress concrete, it is taken Goyan's concrete. Okay. So here is another example. If you on our interest, you can see here. You can see example here, the variation of transverse tensile stress along CC and DD. This is the here, and in view of the beam here, in block is given here, and another example also given here. These are the inlet. So this is the torsional strength. Sorry, this is the anchorage zone. This article is given here. This is the last one, the torsional strength. This is the formula is given here. If you interested, you can take a look. You can see here the ultimate torque for reinforcement and free stress concrete member. Here is the minimum reinforcement is here. X-axis is given this formula, and free stress is dotted at this line, and non-free stress is dotted line, and this is the T value. And interaction curve we've been seen here for combined torsion plus flexural. Here is Bn divided by Bc and Tn divided by Tcr, and x-axis is from 0 to 1, and y-axis is 0 to 1 is given is the curve section. We can use from this formula. What is the mean of T? T is nothing but nominal torsional. Another T is concrete combined, which is reduced TCR, and Bn BCR is Bn is the shear forces failure under the combined, and BC is the laser of BCR. Okay. I hope this the lecture is in depth. So if you have any question, then let me know. I'm just saying again. So these are the important. I'm just saying figure, and then in the math example for shear checking, these are the most important, and this is the another example of the stirrup design. Okay. So all are the taken from this. This is the reference from TY Lean. If you have any question, let me know. I'm just using this note during my classes. If you have any question about new note or something, then you can mail me, or you can what I will say, you can comment in any section anytime. I will try to give you an answer. Thank you everyone for your patience. Thanks.